In our previous videos, we have learned about Norris type 1 reactions and Norris type 2 reactions and beta cleavage reactions. Today we learn about another photochemical reaction of carbonyl compounds, which is called Paterno-Buchi reaction. What is Paterno-Buchi reaction? It is a photochemical reaction. It is a 2+2 cycloaddition reaction between an excited carbonyl compound, that can be a ketone or an aldehyde, with a ground state alkene or alkyne or a diene in presence of UV light, and it forms an Oxetane. Oxetane is a 4-membered ring with an oxygen and 3 carbons. It can be also called cyclic ether. So, Patanobuchi reaction is a photochemical reaction. It is a 2+2 cycloaddition reaction between an excited carbonyl compound and a ground state alkene to form an Oxetane. In this reaction, a 1,4 biradical intermediate is formed. Stability of the 1,4 biradical intermediate determines the product. More stable 1,4 biradical gives major product, whereas less stable 1,4 biradical gives minor product. Stability of the 1,4 biradical also determines the stereochemistry of the product. Patanobuchi reaction is of two types. One is intermolecular Paterno-Buchi reaction. That is, the reaction occurs between two molecules. One molecule is a carbonyl compound and another molecule of an alkene, alkyne or diene. This is an intermolecular Paterno-Buchi reaction. There is another type of Patanobuchi reaction, that is intramolecular Paterno-Buchi reaction. This is given by gamma delta enones. These are the compounds which have a carbonyl group and an alkane in the same molecule. So the reaction occurs within the molecule. So it is called intramolecular Paterno-Buchi reaction. So Patanobuchi reaction can be intermolecular or intramolecular. First, let us see the intermolecular Patanobuchi reactions. Let us see some examples. So, as you know, this is a ketone and this is an alkene. In presence of UV light, a 4-membered Oxetane ring is formed with an oxygen and 3 carbon atoms. This is an Oxetane. This can be shown like this: C double bond O and CH3, CH3, C double bond, this is an alkene. So this is a carbonyl compound, this is an alkene with a double bond. In presence of UV light, this gives Oxetane. And this is a ketone plus an alkyne. Alkyne is, there are triple bond between carbon atoms. In presence of UV light, it gives Oxetane. Here there is a double bond here. Then this is a ketone. This is vinyl alkene. Vinyl alkene. This gives vinyl oxetane. Mechanism of oxetane formation, that is when it comes to symmetrical radicals, that is the alkene is symmetrical. See here, this is the carbonyl group, this is the alkene. This pi bond will cleave to give two radicals, one oxygen radical and one carbon radical. And this pi bond of the alkene cleaves to give two radicals, one on this carbon atom, another on this carbon atom. This is a symmetrical radical because both the radicals are primary here. Now, this oxygen radical will react with this radical to form a bond first, thereby giving 1,4 biradical intermediate. This is 1, this is 2, this is 3, this is 4. This is 1,4 biradical intermediate. In the next step, these two radicals will form a bond. They combine to form a bond and give oxetane. Oxygen with 3 carbons. This is the only product, one product, because there is no major product or minor product, because the alkene here is symmetrical. Okay. Let us study the mechanism of asymmetrical radicals. When it comes to asymmetrical alkene, this is an alkene with CH3 attached here and CH3 and CH3 attached here. So when this pi bond cleaves, it gives two radicals. This carbon will give a secondary radical, whereas this carbon will form a tertiary radical, that is third degree radical. As usual, oxygen will form a radical and this carbon will form a radical. This oxygen is primary radical, whereas this carbon is third degree or tertiary radical, because one R group, another R group and another atom is attached to this carbon, so it is a tertiary radical. Oxygen is a primary radical, so less stable in the carbonyl compound. This carbon is third degree radical, so more stable in this carbonyl compound. So this oxygen is less stable because it is primary radical. This carbon is a tertiary radical, so it is more stable. When it comes to this asymmetrical alkene, this CH3 radical, this CH radical is secondary radical because it is attached to two more carbon atoms, whereas this carbon radical is attached to 3 carbon atoms. So this is tertiary radical or 3 degree radical. So this is more stable. This is less stable. So in the first step, the less stable oxygen radical will combine with the less stable CH radical of the alkene to form a bond to give more stable 1,4 biradical intermediate. So we can say that in carbonyl group, O radical is always comparatively less stable than the alkyl radical. See, this is the oxygen radical, which is always less stable than the alkyl radical of the carbonyl compound. So, oxygen radical is more reactive because it is less stable. It forms a bond with the less stable radical of the alkene. Here, the less stable radical is 2-degree radical, this one. This is more stable radical. So, both the less stable radicals will join together to form a more stable biradical intermediate, which in turn gives major product. Let us see the mechanism. So this oxygen radical is less stable. This carbon radical is less stable. Upon irradiation by UV light, these two radicals will combine to form a bond, as a result of which we get 1, 2, 3, 4. A 1, 2, 4, 1, 4 biradical intermediate, which is more stable, as both the first carbon and the fourth carbon are tertiary radicals. So these two radicals are more stable. So this biradical is more stable. So this 1,4 biradical is more stable and gives a major product. In the next step, these two radicals will join to form a bond, as a result of which we get major product. The oxygen radical can combine with the less stable to give more stable biradical, thereby giving major product. At the same time, it can also combine to a less extent with the more stable radical of the alkene to form a less stable 1,4 biradical, which gives minor product. Let us see that mechanism. If oxygen radical combines with more stable radical of the alkene, a less stable 1,4 biradical intermediate is formed, which gives minor product. So this is oxygen radical, which is less stable. It will combine with the more stable 3-degree radical of the alkene. Okay. In order to make the mechanism easier, let us flip it upside down. So we will flip this upside down. As a result, this is the oxygen radical of the carbonyl compound, and this is the more stable radical has come up and the less stable has gone down. So this less stable and more stable radicals will combine to form a bond, as a result of which we get less stable 1,4 biradical intermediate. 1, 2, 3, 4. This is less stable biradical intermediate, because this fourth radical is a primary radical, whereas in the previous thing the fourth radical was also a 3-degree radical, whereas here it is 1-degree radical. So the less stable 4 radical is primary. So this 1,4 biradical gives minor product. See, this is the minor product. Oxygen, C, oxygen, C, R, R, this, and a CH3 here, 2 CH3s here. This is minor product. So oxygen can combine either with the less stable radical of the alkene to give major product, or more stable radical of the alkene to give minor product. This Patanobuchi reaction is regioselective. Regioselective means The less stable oxygen radical can select one radical of the alkene over the other radical of the alkene to give more stable 1,4 biradical intermediate, which in turn forms a major product. In brief, first the oxygen radical selects the less stable radical of alkene to form a bond, thereby forming more stable 1,4 biradical intermediate. So this is benzophenone, a carbonyl compound. This is an alkene with a CH3 attached here. So this is a symmetrical alkene. So in presence of UV light, an oxygen radical is formed, a carbon radical is formed on the ketone, as well as a carbon radical here and a carbon radical here on this alkene. This is less stable because this is a primary radical. This carbon radical is more stable because it is a secondary radical, because this carbon is attached to two more carbons. So the less stable oxygen selects the less stable carbon radical of the alkene to form a bond. So oxygen and carbon form a bond to give us more stable 1,4 biradical PH, PH, C, O, C, C, CH3. This is the 1,4 biradical which is more. Then the remaining, these two radicals will form a bond to give us major product. So the major product will look like this. These two radicals, this radical and this radical, have joined together to form a bond. This is a major product. For minor product, oxygen radical combines with more stable radical of the alkene. This is the oxygen radical. So let us flip this radical upside down. The more stable radical, let it come up. So this is second degree radical, more stable. These two radicals will combine together to form a bond. So this forms less stable 1,4 biradical intermediate. Then these two radicals will join together to form Oxetane, which is minor product. So Patano-Buchi reaction is regioselective. That is, the oxygen radical will choose less stable radical over the more stable radical to form major product, or the oxygen radical will choose more stable radical over the less stable radical to form minor product. So this is regioselectivity of the Paterno-Buchi reaction. Let us see some examples. This is benzophenone, a ketone, and this is cyclohexadiene, diene because it has two double bonds. Upon irradiation by UV light, this pi bond will cleave into two radicals, as we all know. And let us represent this diene in a different way so that this comes opposite to this double bond, comma opposite. So this radical cleave, this pi bond cleaves to give two radicals. So we have two bonds, two radicals, one radical on pH, one radical on oxygen. This oxygen radical is less stable, as we all know. Here on this cyclohexadiene, two radicals are formed because of cleavage of homolytic cleavage of this bond. This is one radical. This is a second degree radical because this carbon is attached to two carbons. This is also a second degree radical because this carbon is also attached to more carbons. But this radical is more stable because it is in conjugation with double bond. That is, it is an allylic radical. Always remember, allylic radicals are very stable. So, oxygen radical is less stable and this radical is less stable. So, these two radicals will join together to form a bond. As a result of which, we get more stable 1,4 biradical intermediate. This is 1, 2, 3, 4. This is 1, 4 biradical, which is more stable because this fourth radical is allylic radical and it is very stable, right? And this first radical is more stable because it is a tertiary radical. These two radicals will next form a bond to give us major product. So this is how major product is formed. Minor product. How it is formed? First, the oxygen radical combines with more stable allylic radical to form less stable 1,4 biradical. This is the oxygen radical. So we have flipped it upside down, this cyclohexadiene, so that the more stable radical has come up here. That is allylic radical. So these two radicals will join together to form less stable 1,4 biradical. Next, this radical and this radical will join together to form a minor product. So this is how minor product is formed when benzophenone and cyclohexadiene react in presence of UV light. Let us see another example. This is furan. It is an alkene. Oxygen, carbon, 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 double bond here, double bond here. This is furan. It has two double bonds. This is benzophenone. In presence of UV light, one of the pi bonds will cleave to give us a radical here and a radical here. This pi bond cleaves to form a radical here and a radical on this oxygen atom. Next, this oxygen radical is less stable. Now we have two radicals on this compound. This radical is more stable because it is in conjugation with a double bond. That is, it is allylic radical. This radical is also stable, but not as stable as allylic radical. This radical is adjacent to oxygen atom which has lone pair of electrons to donate to form a resonating structure. Still, this radical is less stable than this allylic radical. So, allylic radical is more stable. So, what happens? The less stable oxygen radical will combine with this less stable radical next to the oxygen to form a bond. So, let us flip this carbonyl radical upside down. So as a result of which the oxygen radical is here and the less stable radical is here. These two radicals will join to form a 1,4 biradical, more stable 1,4 biradical. 1, 2, 3, 4. 1,4 biradical. Then these two radicals will join together to form a bond here. This is the major product. Let's see example 3. This is another alkane with a nitrogen heterocyclic compound with a nitrogen in the ring. So here there is a double bond. This is benzophenone. Upon irradiation by UV light, this pi bond will cleave homolytically to form two radicals. This pi bond also cleaves to form two radicals, as a result of which we get oxygen radical, which is less stable, and a carbon radical, which is more stable in benzophenone. And here we get two radicals, this radical and this radical. This radical is more stable because of the lone pair of electrons present on the nitrogen atom, which can be donated to form a resonating structure. So this radical is more stable, this radical is less stable. So the less stable radical of this alkene and the less stable radical of oxygen will form a bond. So we get 1,4 biradical, that is more stable 1,4 biradical intermediate. Next, these two radicals will combine to give us a major product. So this is how we get major product here. Let us see another example. This is benzophenone, this is a diene. So this is a symmetrical diene because there is a CH3 group here, CH3 group here, carbon, double bond carbon, carbon, double bond carbon, and CH3 group here, CH3 group here. Upon irradiation by UV light, this pi bond cleaves homolytically to give us two radicals, and this pi bond or this pi bond can cleave. Either way there is no difference because it is a symmetrical molecule. So here we get a radical and here we get another radical. Now let us see what is the importance of these radicals. This is oxygen radical, which is less stable. Okay, here this same compound is represented in a cyclic manner so that the reaction can be represented easily. So there is a radical on this first carbon, a radical on the second carbon. This radical is tertiary radical and the radical on the second carbon is a secondary radical, 2-degree radical, but it is more stable because it is in conjugation with a double bond. So the next carbon atom has a double bond. So this radical is more stable. In other words, it is an allylic radical. Allylic radicals are more stable. So the less stable oxygen and the less stable radical on the carbon will join together to form a bond, and a more stable 1,4 biradical intermediate is formed. Now next, these two radicals will join together to form a bond, as a result of which we get an Oxetane, substituted Oxetane, which is major product. Let us see another example. This is a cyclic alkene. So far we have seen only alkenes. So this is a cyclic alkene, this is a carbonyl compound. It has a double bond here. So upon irradiation by UV light, this pi bond will cleave homolytically to give us two radicals. This pi bond between oxygen and carbon also will cleave to give us two radicals. Let us see what it is. So we got two radicals here. One radical on this carbon atom, one radical on this carbon atom. This has an alkyl group attached to it, this has an alkyl group attached to it, and another carbon atom attached and another oxygen attached here. So here this radical is more stable because the adjacent oxygen has lone pair of electrons to donate to form a resonating structure, whereas this radical does not have such facility. So this radical is more stable. This radical is less stable. So the less stable oxygen radical and the less stable radical of this compound will form a bond. So we will turn this structure upside down so that less stable oxygen radical and less stable carbon radical will come together and they form a bond to give us more stable 1,4 biradical intermediate. In the next step, these two radicals will join together, giving us a cyclic product, which is major product. Okay, this is the product. Let us see another example. This is a ketone, that is benzophenone. This is alkyne. C triple bond C, R and R here. So this is a symmetrical alkyne. Upon irradiation by UV light, this pi bond cleaves, forming two radicals. We know that. In this triple bond, one bond will cleave to form two radicals. One on this carbon atom, one on this carbon atom. Since it is a symmetrical alkyne, this less stable oxygen can combine with this carbon or this carbon radical. There is no difference. So let us combine these two. When these oxygen and this carbon atom combine, we get a 1,4 biradical intermediate. In the next step, these two radicals will join to form a oxetane ring, that is oxetane with a double bond in the ring. This reaction will not stop here because a double bond puts strain on the ring. So ring opening occurs, as a result of which this double bond, one of these bonds shifts here and this bond shifts here, as a result of which we get O double bond C and R, single bond C, C double bond C, PH, PH and R. This is the only product in this case. So when an alkyne reacts with an excited carbonyl compound, we get first an oxetane, which on further reaction gives us a product like this without a ring. The ring opens due to strain of the double bond in the ring. Now let us see the stereoselectivity of Patanobuchi reaction. Alkenes with electron donating group substitution gives cis trans isomers upon reaction with carbonyl compounds. A cis isomer gives trans isomer as major product and cis isomer as minor product. Trans isomer gives cis as major product and trans as minor product. In short, we can say cis gives trans as major product. Trans gives cis as major product. When the alkene is substituted with electron donating groups. So, when an alkene with electron donating group is reacted with a carbonyl compound, cis gives trans as major product, trans gives cis as major product. Let us see, take an example. This is benzophenone, a carbonyl compound. This is an alkene with methyl groups. Methyl groups are electron donating groups. Since both the methyl groups are on the same side, this is a cis product, cis isomer. Upon irradiation by UV light, an oxetane is formed with methyl groups, one above the plane, another below the plane, that is trans isomer as major product, and another oxetane with one methyl, both the methyl groups above the plane or both the methyl groups below the plane, cis isomer as minor product. Let us see the mechanism. This is the carbonyl compound. pH, C double bond O. It is in ground state. When it is irradiated by UV light, it undergoes N to pi star transition and enters singlet state. In the singlet state, this pi bond cleaves. So as a result of which, a radical is formed on this carbon atom and a radical is formed on this oxygen atom. So the electron of this radical is in clockwise direction and the other electron is in anti-clockwise direction. We know when a bond is formed, two electrons are involved. Thus two electrons will be in the opposite spin. So these two electrons are separated now. They are still in the opposite spin. So this is the singlet excited state. Then this singlet excited state through intersystem crossing enters triplet excited state. In the triplet excited state, both the electrons will have the same spin. Okay, both the electrons are in the same spin. Now, to this excited carbonyl compound, this cis alkene is added or it reacts. So, this pi bond between this carbon-carbon double bond breaks, forming a radical on this carbon and this carbon. One electron in anti-clockwise and another electron in clockwise spin. So this electron, clockwise spin electron and anti-clockwise spin electron of the carbonyl group will join together to form a bond. As a result of which we get a bond between these two. So a 1,4 biradical is formed. But this carbon's electron and this carbon's electrons are in the same spin. Since both the electrons have the same spin, there is no bond formation. Then there is no bond formation between this electron and this electron. Now two processes occur. First process is spin inversion. In spin inversion, one of the electrons will change. This electron or this electron will change its direction. Let us take this electron has changed its direction to the opposite side. So this electron and this electron have opposite spin. So bond formation occurs, giving us a product. Now here cis isomer is formed. Why? Because in the beginning this was how it was. CH3 on the same side, same plane, and here also CH3 on the same side, same plane. Here also same side, same plane. So this is cis isomer. This is a minor product. In the second process, this bond between this carbon and this carbon will rotate because it has become a single bond after breakage of this bond, double bond. This single bond can rotate. So it rotates. Thereby the groups will exchange places. CH3, which was on this side, has gone above and H has come down. These two groups have reversed their places, but the electrons have the same spin. Next, these two electrons cannot form a bond because they have the same spin. In the next step, spin inversion occurs. So the electron has taken opposite spin. This electron in the opposite spin. So both these radicals will form a bond, as a result of which we get major product. Why major product? Because CH3 is on the opposite side of this CH3. So this is a trans isomer. Trans isomer is major product. Why? Let us see why. Cis isomer of electron donating group substituted alkene gives trans isomer as major product because bond rotation of 1,4 biradical intermediate occurs very fast, faster than spin inversion of the 1,4 biradical. So the above plane group goes below the plane and below the plane group goes above the plane. So stereochemistry is reversed. Because of the bond formation, bond rotation, this stereochemistry is reversed. So cis becomes trans. So trans is major product here. If we have taken trans alkene, the cis product will be the major. Now let us see stereochemistry of electron withdrawing groups on the alkenes. So this is carbonyl compound, benzophenone. This is a cis alkene with electron withdrawing group as cyanide, CN. Cyanide is an electron withdrawing group, cyanide. So both the cyanides are on the same side. CNs are on the same side, so it is a cis isomer. Upon irradiation by UV light, we will get cis isomer as the product because cyanides same side. Okay. So when it comes to electron withdrawing groups, cis will give cis isomer, trans will give isomer. Trans alkene with electron withdrawing group, CN on opposite side of the double bond. They will give one above the plane CN and one below the plane CN. So this is trans isomer. Trans isomer gives trans isomer, cis isomer gives cis isomer. Let us see the mechanism. This is the alkene. This is the carbonyl compound in ground state. Upon irradiation by UV light, it undergoes N to pi star transition and enters singlet state. In the singlet state, one electron will be clockwise, another electron will be anti-clockwise. So they have opposite spins. Then this compound through intersystem crossing will enter the triplet state. In this triplet state, both the electrons have the same spin. To this, the alkene with cyanide groups, that is electron withdrawing groups, is reacted. So this carbon has an electron in clockwise direction. This oxygen has electron with anti-clockwise spin. So these two will form a bond. So we get a 1,4 biradical intermediate. This carbon's electron and this carbon's electron have the same spin, so they cannot form a bond. Spin inversion occurs, as a result of which this electron spin is reversed. So one electron in the upward, one electron in the downward. So bond formation occurs, forming another bond between this carbon and this carbon. This is the cis isomer. This is the major product. So when an alkene with electron withdrawing groups is reacted with carbonyl compound, cis isomer gives cis isomer, trans isomers gives trans isomers. Whereas when an alkene with electron donating group is reacted, cis isomer gives trans as major product, trans isomer gives cis as major product. In summary, let us see the same points. Alkene with electron donating group gives both cis and trans isomers. Trans gives opposite isomer, that is cis isomer as major product. Cis gives its opposite, that is trans isomer as major product. This is due to bond rotation occurring in alkene with electron donating group upon reacting with excited carbonyl compounds. This bond rotation occurs faster than spin inversion, as a result of which the bond rotation product, that is trans product, the trans product will be the major product, or the cis product will be the major product. Whereas spin inversion occurs slowly. So the opposite isomer, this will be minor product. Alkenes with electron withdrawing group give the same isomer. Cis isomer gives cis isomer, trans isomer. This is because there is no bond rotation occurring in alkenes with electron withdrawing group reacting with excited carbonyl compounds. So bond rotation does not occur when an alkene with electron withdrawing group reacts with excited carbonyl compound. In short, we can say alkenes with electron donating group give opposite isomer as major product. That is, cis gives trans as major product, trans gives cis as major product. Alkenes with electron withdrawing groups gives same isomer. Cis gives cis, trans gives trans. Now let us see what is intramolecular Patanobuchi reactions. Gamma delta enones show intramolecular Patanobuchi reactions upon irradiation by UV light. This gamma delta enones have the same molecule contains carbonyl group as well as alkene. When irradiated by UV light, carbonyl group is excited to triplet state, whereas the alkene is in ground state. So the carbonyl group which is excited to triplet state reacts with ground state alkene to form a oxetane. Let us take an example. CH3, C double bond O, CH2, CH2, CH2. This is carbonyl group. So this is alpha carbon, this is beta carbon, this is gamma carbon, this is delta carbon. So this is gamma delta enone. Upon irradiation by UV light, this gamma delta enone, this bond between oxygen and carbon cleaves, giving us two radicals, and the bond between alkene cleaves to give us two radicals. So there is a bond, this forms two radicals, this bond upon cleavage forms two radicals. This radical on the oxygen and this radical on CH2 join to form a bond. So we get a ring structure. Now in the next step, these two radicals will join to form a bond. So this is the only product which is intramolecular Paterno-Buchi reaction. This has two rings with an oxygen here and other CH, CH2, CH, CH2, CH2, CH. Let us see another example of Patanobuchi reaction. So this is the carbonyl group with CH3 attached here. 1, 2, 3, 4 carbons, and there is a double bond carbon here. So this is alpha, this is beta, this is gamma, this is delta. Let us represent it in a simple way. So this is C double bond O. This is CH3. This is the first carbon. This is the second carbon. This is the third carbon. This is the fourth carbon. And this is the carbon double bond. Upon irradiation by UV light, this pi bond cleaves to form two radicals here. One radical on this oxygen, one radical on this carbon atom. This pi bond also cleaves to form two radicals. One on this, one on this. This is less stable because this is a primary radical. This is more stable because it is secondary radical. So the less stable and the less stable oxygen radical will join to form a bond. So we get 1,4 biradical. In the next step, these two radicals will join to form a bond, as a result of which we get major product. The major product looks like this. That's all for now. Thank you for watching. Please subscribe, share and comment. Thank you. Bye.